Welcome back to Cloud Computing and Big Data. Today we have our lecture 13. That is about OpenStack Cloud Operating Systems. So that's an interesting topic because we switch the perspective a little bit that we had before in previous lectures, where we think about much more today how we actually build a cloud if your boss comes into the room and says, we need our own cloud in the house. And you would think, okay, that's not that easy to build. But basically, what we learn today in this OpenStack environment is that there are lots of components already out there in an open source toolkit that basically can help you to create your own cloud. And that is actually also partly really compatible with the public cloud offerings. So that is a very powerful tool. And some of this you already experience a little bit by using the HDF cloud. Of course, you don't really notice that, because all of that is hidden more or less from the users. However, here the perspective of lecture 13 is really thinking about that you're now in charge of creating your own cloud on-premise in your own basically company or research organization in order to basically leverage that open source component. This is something where you really think about OpenStack. However, before we move on to lecture 13, let us review what we had the last time, which was basically about containers and Docker. And we learned basically in this lecture that despite we have the power of virtualization that introduced us to the idea of hypervisors and then having different images which always feature a guest operating system with some binaries and applications that we basically see a little bit here, we learned that basically there's also one other paradigm which is often used in cloud deployments, called basically the containerized applications that you see here a little bit. So in a way, you would say they're very compatible. There's basic infrastructures, both need that. You have a host operating system, both need that. But of course, the hypervisor technology is a little bit different than the Docker engine. And that's what we learned last time, where hypervisor always kind of this operating system calls coming through the hypervisor. And the virtualized calls are then, of course, getting to really physical hardware. Still, what you carry around always was this guest operating system, which of course means a lot of storage, lots of overhead. The images are still quite successful, so I'm not saying this is a bad model. You have seen in the AMI from Amazon Web Services, for instance, there's deep learning packages that have lots of different, deep learning packages in very specific versions already bundled for very specific applications. But there we have always the, let's say, Amazon Linux or some other Linux that we carry around. In the Docker idea, this is all a little bit different. Although you abstract still from the host operating system and the infrastructure underneath, the idea of the Docker engine is more about thinking, can we have some recipe or some kind of more standardized way of basically shipping applications out. And what we have there is a Docker file that already says what are basically the ingredients of this containers. And with this, it pulls the resources. And in a way, these kind of applications with the binaries suggested here are much more lightweight because they don't carry around some guest operating system. Instead, they really focus on the applications, focus on the data sets maybe that are shipped. And the benefits you have if you follow, for instance, the Docker engine, which is one of the more or less de facto standards today in terms of containerized applications, you have a standard way of doing so. So when you have this ship analogy that you see here, right, where lots of containers know exactly where they are and they basically fit to each other, and the containerized application approach here probably has some interesting economics of scale. If you think of a big ship, know exactly how to scale out, so to speak, to a big ship. Hence, there are lots of container benefits that this suggests, because you have a consistent runtime environment in these containers. More or less, the applications are still sandboxed, so they are on their own in these containers, very well, encapsulated from all the other applications, and being in isolation, which is considered to be quite a good approach if you don't want to intervene with other applications. And given that guest operating system is not carried around, we have a relatively low overhead and small size on disk. And thinking about the Docker engine is then basically also pulling some of these binaries and libraries. When you basically instantiate these kind of Docker containers, it's really low overhead to basically go for. And the virtual machines, in one way or another, have some of these benefits, but not all of that is really true, particularly if you think about the sizes and the idea how you manage them in terms of overhead. Then when we want to go big scale, we also learned in the last lecture, containerized applications need a certain way to scale out. And what we learned there was a little bit like Kubernetes, kubelets, having Kubernetes nodes to actually do the job in combination with Docker in order to fill a whole cluster. And that's what we are interested in, right? In the cloud computing course, especially how we do really scale out to many different nodes. And that's where Kubernetes comes in. And we also learned that actually here and there, you really want to combine maybe even public cloud offerings with some of other cloud offerings, and where you can have portable solutions, just porting your Docker containers from one infrastructure to another. And chances are that this really works quite well, because as I said also earlier, the Docker environment is quite a standard and in a way really adopted by Amazon Web Services, MS Azure, Google, and many others. Now, this is a key idea, and with this you have lots of these features that you derive from Kubernetes directly for your cloud. We also learned that basically by an example that containers still are on their own, and hence you need some management approach on it. So I think Kubernetes is one way of deploying it, but still you need the whole management infrastructure. And this means it's a little bit more than just thinking Kubernetes. You want to know which of these different containers are existing, right? Think about the ship analogy again. So there should be several containers on that ship. What is the registry? What are the different types of containers being there? Is it AIM-SCIP, Maersk, or anything else? And we took particularly the idea of, basically the Google Cloud here in this lecture last time to also make the note of course, containers evolve in time. There are codes. Their code inside, there are different data sets inside. And I think one of the good ideas of this Google Cloud is if you use it, that they actually can support the kind of development process, the cloud build process around containers quite well, to really have this containerized applications we're talking about today, supported in different versions and so forth. So something that not need to be forgotten, as you would basically suggest, again, if you think about the analogy of the containers, right? So there's a ship and there's containers. You don't want to have some container that is never opened, never used for a long time. You don't want to have outdated containers, and everything in this is basically around this runtime, and container registries can help to keep track, to maybe remove some of the old containers and think about also some new containers to evolve. Now, in terms of containerization, in terms of using Kubernetes at scale, we learned further in the last lecture that there's this kind of opening a kind of unique niche market ideas, because basically here you now have a very good idea of deployment at scale with Kubernetes. You have a more or less de facto standard way of describing your applications in Docker. So with this, you basically have lots of deployment activities already delegated to the cloud in a way. And all you need to do is basically having an on-top application that really leverages all of this flexibility. And we learned that Cookpad, in a way, was basically one of these examples. We have an app that really needs to scale up very quickly, scale down very quickly, depending really on the load of the application. TV commercials, TV basically can really increase the usage of an app significantly, where you have this typical cloud elasticity that we described already in previous lectures, to be there on time and at the right time of the day. And by looking also on other cloud offerings, we looked at the Uber Cloud, which is basically very specific for engineers. You find that the niche market they serve is a specific set of packages like Siemens, Ansys, OpenFOAM, and many others that actually are on top of this containerized scale-out infrastructure based on Docker and Kubernetes, but focus on a very specific niche market, if you want, on engineers that really need this high performance computing in the clouds today. And this was the Uber Cloud we learned last time. where you have basically different cloud providers underneath, from Amazon, Microsoft, Google Cloud, HPE, whatever it is. But the key message to take away is you don't really focus on that very much, because you base yourself on the idea of Kubernetes and Docker. And this is very powerful and admittedly also adopted by many others, like for instance, Rescale is another basically provider that has very similar ideas with packages on top of containerized applications, on top of kind of Kubernetes and HPC. And here you definitely find a new market, so to speak, that leverages really the container approach and Docker. However, let us go then proceed now to the lecture idea of today. And here's the really idea of shifting the view a little bit, thinking about the scalability challenges that we have basically in clouds today, especially if you think about that you now in charge in your own company to build such a service in-house. And there it's basically good to see that the idea of combining these different cloud offers today is basically the modus operandi. So you would find many public, private, or hybrid cloud building blocks that are put together in order to solve application domain problems. And I will pick just several pieces out of the OpenStack larger set of services to focus really on the key paradigms that we already learned in this course today. And basically, in the past, when you think about that, we had object storage, block storage, and other elements in terms of storage services or compute services that should interact with some containers. So you see, basically the principal idea of recreating a cloud, but in-house, is already there. So there are building blocks that I will talk about in the first part of the lecture. In the second part, we again would pick some, let's say, advanced functionalities and provide some examples, because you can imagine that something which is as powerful as OpenStack would normally require 2, 3, 4 university lectures or a complete training from morning till evening for at least 3 days to really have OpenStack completely understood and taken on board on your own applications. Hence, we focus here on some highlights, if you want. Again, making the case of Kubernetes and sample configurations, if you want, for instance, connect to what we had earlier in the course with Hadoop clusters. There's an API access and basically a whole SDK around this OpenStack that we will discuss briefly in the second part. And then it's all about sharing, thinking, and basically getting ideas of how you can contribute to the larger community with marketplaces. And we will review some of the business cases where you really think that people have adopted this OpenStack with basically cloud offerings. There's some different application examples, we will talk about it. Apart from the commercial ones, we also briefly again review the Helmholtz Data Federation that you already know from your assignment. So let's dive a little bit into OpenStack. Basically, again, always think about now that we shift a little bit the view, so we know there are different clouds available outside. We said in the containerized applications example already, yes, we know we basically have the Google Cloud Platform. We know about Amazon Web Services, which are other clouds here, which basically fuel your app with some specific application parts, and you use Kubernetes to orchestrate and manage them all. And today we will basically think a bit much more on-premise. So we get away from the public clouds that we know, but rather thinking about, as I said earlier, someone in the decision-making in your own company decides, now it's time for the IT people to really create their own data center and your own cloud. So what we do there, and the answer is, think about OpenStack. Before you potter off and recreate all the different services needed to manage computing, schedule resources among basically resources that are shared with many users. And you can go on and go on. The storages we talked about, object storage, file storage, block storage, etc. These are all topics which are taken care of by software components that you can actually use. And here, this OpenStack is not just one of those different open source projects. Here you could actually highlight that it's actually part of the Open Infrastructure Foundation. In other words, it's really one of those top-level open infrastructure projects, which are really, let's say, more or less production quality. So this is something to really look at before you really create your cloud on completely on your own. So there are different components that you always need in clouds for computing, for storage, for networking services. And this even includes some APIs that you need in order to integrate better, perhaps, with your applications. And on top of it, also enable here and there the interoperability with the public clouds that is often needed also. If you think about peak times, if you think specific services in AWS that you really want to use, basically on top of your own data center or on-premise cloud. Hence, we shift the view indeed of saying, what happens if you are in charge and create your own cloud, which of course, still remember, requires some form of physical hardware. So you don't start from zero and then suddenly use OpenStack. OpenStack needs to be deployed in context of some, physical hardware that still needs to be existing. This can be virtualized and should be virtualized, as this, graphic suggestion that I already in the course have pointed out many times. And what OpenStack is now helping, it has all these different components around it that really make it basically an interesting deployment model for all of these higher level services that you would always need to manage the virtualized kind of resources in terms of computing, in terms of storage, and of course also networking. And what we learned in the last lecture, this also includes, of course, containers and much more topics like security we really didn't make a big fuss on in this different course hours here. So hence, the OpenStack source software, as I said, there are lots of different services. You could have a training at least for 3 days, maybe not a complete week would be appropriate. Hence, still of an OpenStack perspective, you always have to think about that there's this interesting idea of having still some resources available. And I think this is very clear to say that this is a, let's say, software management infrastructure. You still need the physical hardware, like if it is bare metal, if it's virtual machines on top of these bare metal services, or containerized applications, as we learned in the last lecture. So we don't go around that. And with this, build the foundation of, let's say, the standard hardware needed by an OpenStack shared service infrastructure. And there, the key fundamentals, you would say, is we have this compute services, network services, and storage services that in one way or another should be basically part of an API that you can use within your applications to cloudify them or to really leverage your on-premise cloud. Now, when you think about, of course, there should be an overview as well, so you can add on to more and more services. Hence, monitoring, as we learned, is a very important part of it. Is a service still up and running? If you're in charge of your own cloud, you want to know basically what's the upside of the cloud, what basically is the idea of how many, basically failures I have, where are problems in the infrastructure I provide to my own company, because chances are that other divisions will come to you as an IT division and then will be very unhappy because your downtime is, let's say, very high. Your systems are not accessible. And so you need to have this OpenStack dashboards and their services around this. And the idea there is really to manage and control and have an overview of many of these compute, storage, and network resources you really have then basically created and maybe shared within your own organization across different organizational boundaries, perhaps even as well. And the interesting thing is that these services are inherently designed to be scalable. And here comes a cloud paradigm and also the idea of why you should rather look into OpenStack when you need to build your own cloud instead of creating, your own Java components, modules, or even C#, whatever programming language it is. Chances are that by recreating these services, you do some errors. They're not really scaled by design. And basically, as being open source, nothing prevents you from just using these services in production, especially as many people have done so already. What I want to bring here shortly with this particular slide. Many of you know these companies. I think Blizzard Entertainment stands for itself. It's a very strong idea of, a gaming company that, of course, needs really quite of an interesting scaling infrastructure. You have to scale with your number of users. And Blizzard is very well known for World of Warcraft, is basically known for large games, big games, large user communities in terms of gamers, where you really have to scale up your infrastructure up and down with the requirements in order to really have, let's say, a good idea of using these services, because you want to make your customers happy, right? And you can imagine that for someone with Blizzard, with a huge reputation of good games, that is something to lose. So basically, they build on OpenStack and the auto-scaling infrastructure to really keep the video games running at a very good performance. And of course, this is a gaming industry. We have also the retail industry that basically have also done lots of elements using OpenStack clouds for different purposes. So here it's basically also to think about how can, let's say, other organizations that are not IT also benefit from cloud resources, and Walmart is a very good example. Then when you think about China Mobile is another good example where OpenStack is adopted, and of course you can go on and go on. I will not talk too much deep into it. There's an OpenStack website that apparently have all of these success stories basically already described very nicely. And you see that it managed around 20 million cores around the world in many different industries, including what you use for your assignment 3, the HDF cloud, because if you look at the paper around it, it is basically an OpenStack-based infrastructure as a service environment. And here and there, you would say today it's even partly platform as a service, but still the message is basically many of these cloud services today that are available are in some way or another built on different OpenStack components. And this we try to understand, again, thinking about more the scalability, which is more important in these data centers. So these are components which are not just from software engineering, basically designed to say we solve that problem of submitting to compute. Here the idea is how we can do scalable solutions. And here the size matters in terms of scalability. So there we want to scale up and down with the availability of cluster components. And then of course also with the software scalability, what about different libraries that we already know from deep learning, for instance, are required for different packages, and then also thinking about the versioning over time. So hence, there's lots of these elements which we can cover with these technologies, including application scalability, where basically we also want to go up and down with the application size that could even affect the data, which is alongside it. And this is something where you can, of course, thinking about the application itself, how it scales. And then technology scalability is, I think, also pretty obvious, where you basically have different components available at different points in time, that you want to make sure transparent with the OpenStack components, that they are supported, that they can be added, removed at any point in time without breaking the larger functionality. So this is basically the probability then to having a system very nicely built on OpenStack, which, so to speak, adapts to the changes that will apply when you add new technologies, when you add new applications. And this is a very important factor, because you don't want to spend more and more time of just thinking about the scaling. This is something what these components are already, so to speak, designed for. So when you look at this from the service landscape, obviously, as I said, I could talk a whole week on it. The OpenStack seminars even go for multiple weeks, and you could have 3-4 universities lectures. Hence, you see they have different elements in terms of client toolkit, solutions, a command line interface, as well as a software development kit, the integration basically of different services. But key to the point is still the compute services in red, the networking services, hardware lifecycle, storages, things we already know. And of course, also then the idea of doing some, let's say, monitoring with the horizon components, with web front ends, and then being also here and there able to orchestrate services with heat and others, which we will look into it. Hence, you see sort of a Lego brick idea again. So you have on each of these different levels, different services which are known, like Nova, for instance, managing virtual machines, Sun for containers, and so on. So this is something what we basically want to maybe combine with some storages, and also type of storages already known to you from the Amazon world, if you remember, object storage, block storage, file storage, and they just have different names here, which is Swift, Cinder, and Manila. This should be going to, of course, some security components like Keystone and Storm, in order to really make it then able to use OpenStack, combine these different services, and then deploy your own application in the so-called on-premise cloud if you want, but being still interoperable, maybe through API proxies with the EC2 interface or S3 interface design, which is also possible for storage in order to still interact with public cloud offerings. So very powerful tool set where basically we just pick a few here in the course today in order to make the case why OpenStack is quite nice. I think one of the key suggestions that we had very early in the course, which makes differentiations now between high performance computing perhaps with static resource sizes, is a little bit the idea of having this elastic load balancing services. And particularly this auto scaling, where you don't want to be in charge of monitoring maybe every single hour what's happening on the cluster, if the capacity has been reached, if you want to add some node, if you want to remove some node. It's all a question of this kind of scaling. But if you think about it, that having an operator just looking at this all the time, he would be still quite, not really, not only bored, I would say, but also being a big cost factor, while here the idea is to do auto scaling. And auto scaling means that the systems cannot go up and down in scale. And this is automatically done, not needing necessarily an operator, perhaps still someone on the quality of service level, checking every now and then what's happening with the cloud. And this is something where, let's say we come back to this OpenStack components. They're inherently designed for actually doing this with a couple of services you have to add. You see here a little bit how you would basically have a compute component called Nova in a way used to really manage the different, let's say, virtual machines in the system. And you need basically the service component to have, let's say, really compute services which have been on different levels here. But you see also that in order to just compute with the hypervisor, you need different components like a Neutron, maybe for security, and Keystone. We need APIs, a scheduler, and of course thinking about the placement of the computing entities. The Nova compute service is basically helping a lot with this by still being very much, let's say, interoperable with the other components of the kind of OpenStack framework, which of course can help now in the idea of really scaling up a lot. And these building blocks are really something which help you a lot with different codings, which otherwise you have to implement really, bare your hands. And this could be very challenging and time consuming and eats up a lot of resources, especially for, let's say, an SME that maybe decides an OpenStack cloud in-house would be still very nice. So in order to do this, then basically this auto scaling that I mentioned is inherently in the design. So you see here a little bit while we have the hypervisor, we see images from the Nova service. The computing will automatically be able to scale out and scale down, and having then basically this idea of a kind of elastic services. But still you have to do a conductor. It's not that easy that you just have one little service throwing on the problem and everything works by magic. You see definitely the idea of having different, let's say, components of this framework from OpenStack heavily intertwined with each other, from even including, of course, also the database where the images are stored, if you talk about basically virtual machines in terms of Nova. So people that adopt that and organizations that adopt this are basically often having the idea of some security concerns. Here's an example of a Volkswagen group that obviously has lots of data about the next kind of fleet of services and fleet of actions in terms of car design, in terms of car manufacturing. So these are all more or less secrets which are often kept in kind of, let's say, more on-premise clouds or private clouds, while many of the mathematical models here and there you can learn from are maybe something you first compute in the public cloud and then take it to your local offerings. So here's one example we already discussed in one of the previous lectures, who are actually also adopting OpenStack as part of the infrastructure as a service platforms and private cloud, so to speak. Then also thinking about what we discussed the last time, that maybe with Nova, that's not enough. So having just computing and virtualization, that's what we just had in a couple of minutes ago, realizes the left-hand side. And I mean, this could be lots of different applications that leverage traditional virtualization techniques. So nobody says that this is definitively a bad approach. There could be good reasons why you want to have this virtualization approach, especially if you want to have functionality adopted in different guest operating systems, but also basically being interoperable with the larger virtualization community that often has images to share and then to compute. On the other end, we said in the last part of this, first part of the lecture, containerized applications have quite some good benefits. Firstly, this low storage footprint, but also, of course, thinking a little bit with the analogy of the ship, you're sort of vendor lock-free. So what I mean by this Maersk line could also take on Imeskip container, can take on Maersk containers, Smurl line containers, because they're all more or less following the idea of this kind of containers. And of course, this is something where you basically go into the area of a SAN service. So it's not only Nova that needs computing, which is basically always needed. You need also something which is executing containers, where then SAN is good in another kind of component out of the OpenStack framework. So you see quite an interesting component for all of the different levels we have in terms of using it as a cluster really for scaling out. And you see here how the SAN service roughly works. You basically have, again, the idea of combining this, of course, with many different services like Neutron on the network security and others. And also, of course, thinking about the image of the virtualization part that needs to be stored somewhere. So there's a glance service that, of course, represent then the idea of the image at the point in time where basically SAN then come into place and want to put an instance to the computing, and then also thinking about having a Docker instance then that is pulling all from the Docker file, all the libraries and elements really of your application that is needed. So still, it's a very lightweight containerized approach. Still, you need to combine it with different services, as we discussed earlier. And of course, you have different ideas than basically we have also seen in the AWS cloud, different containerized applications, components that you can leverage. And this is, of course, also true for the OpenStack Purion, which is basically an idea of really more on the network level support with containers. So you find very different components, which is then really the idea of showing you this. While, of course, many of these components that you already know with Nova and SAN compute, and these are really often used in many applications, including glance for storage maybe. So coming then basically to the storage domain a little bit more, this is a slide you already know, so I go quickly on this. You remember the bucket store idea that we had here with the so-called de facto status S3, a kind of bucket where you put in different data with more key value based approach, having different APIs supporting this, most notably the REST interface. So by thinking about this, there are different ways how you really can connect to basically these ideas that we described earlier. There's elastic block storage as well that we had discussed in one of the lectures, where you see basically lots of different prices will come, of course, now into the game when you talk about storages, when you also talk about how long these storages should be used, how they are attached to the different services, and so forth. So in a way, we see here the motivation for some of the services we have in OpenStack, right? So Amazon obviously has similar services that in a way we want to reproduce in order to create our own cloud, being independent from AWS. Hence, we still notice that with the block storage or the elastic block storage, with the object storage, the different types of services we still want to connect. Hence, we need these building blocks And they are often models a little bit like we have seen also in Amazon, MS Azure, or the Google Cloud Platform. So it's no surprise that basically you find different components that we had also discussed in one of the AWS lectures recently. Again, thinking about file system ideas of storage, the block storage idea, but also then object storage where the Amazon S3 is really important. So this is basically a one-to-one mapping. And I think that's something what you see here already when we maybe take the most crucial components in the OpenStack component set, what we so to call also core components, which are read here a little bit, where Nova Computing, Sun for virtualization for containerized applications, need to also be supported by the lower level parts like networking, hardware, but most notably also storage. So it's a one-to-one method of the storages we have seen in Amazon, partly in MS Azure, where we say here we have an object storage based on Swift, we have a block storage based on Cinder or file on Manila. And these are rudimentary blocks on their own. They're quite often not really used. So you really, again, put them in the OpenStack infrastructure, build an infrastructure, if you want, based on OpenStack, depending on the requirements, of course, on your users within the companies. Do they require a big infrastructure for containers, a mix of virtual machines and containers, or even are some people very keen of having just bare metal access, or basically all of them combined? It's up to you to define these things. The point is just that you have the software infrastructure components there that nicely interact, and you don't have to redevelop over time in order to make these deployments. And in a way, that's firstly the introduction, basically why OpenStack is so useful. It has lots of components. And I think I show you this also as a summary here before we close the first part of the lecture in a small video.
Organizations today have to bring new services to market faster. That's just what it takes to stay competitive. The pressure on IT departments and operations teams to do this is increasing, and it's coming from all angles of the organization. Your business needs greater agility and scalability from IT to bring new services and applications to market faster. Your developers need greater platform availability and faster resource provisioning, along with multiple environments in which to test new applications. To meet these challenges, your IT infrastructure must evolve. It has to become more efficient, agile, and scalable. This is how you become a true digital business, improve your bottom line, and prepare for the future. So, how can you get there? With OpenStack. OpenStack is a cloud framework providing agile, scale-out infrastructure. OpenStack can power standard cloud computing services like compute, network, and storage resource provisioning, and self-service automation that administrators and users interact with directly, freeing your IT staff to focus on more strategic activities. By bringing such public cloud capabilities to your data center, these key cloud services can independently scale to grow with your demands. OpenStack is open source. It's built on open industry standards and APIs, so it's highly adaptable, and you don't have to worry about vendor lock-in. OpenStack is reliable and secure. Data and applications are built, tested, and stored in your cloud behind the security of your firewall. OpenStack is proven. Based on a community development model backed by tens of thousands of developers, OpenStack has helped public and private organizations across the globe solve their critical IT challenges. Learn more about how OpenStack can bring agility, efficiency, and scalability to your IT infrastructure.
Okay, so needless to say, I'm not paid by OpenStack in any way, or Red Hat or so, but I think it's a good video to show you a little bit and summarize what we can do with OpenStack. Well, in the second part of the lecture, we will basically here and there pick some advanced functionalities and provide you some application examples. We break here for a short time. See you then.